Hello everyone, hope you're all doing well today and thank you for joining today's webinar. We're just going to wait a couple of minutes before getting started to allow everyone who has signed up time to join, so please stay tuned and we will be kicking off shortly. Hi everyone, we are ready to get started. So thank you again for joining our webinar today. My name is Alice Holt and I work in the marketing team here at EDB. And I'm joined by Michael Willer, who is our lead sales engineer in EMEA North. Before we get started, there's just a couple of housekeeping items. The first point to be aware of is that we are recording and we will be sharing the recording alongside the slides after the webinar. And secondly, the lines are currently muted. So if you have a question, please submit it in the Q&A question panel and there will be time at the end for Michael to answer any questions. And that's all from me. So I will hand over to you, Michael, to begin the webinar.
Thank you very much. Michael Villa. I live in Copenhagen. I'm a sales engineer. I've been with EDB for 2.5 years, which means that as I always say on customer calls, I'm a techie, but there you go. Okay, so the agenda for today, as has been announced, how physical and logical replication works, differences, the advantages and disadvantages, uh, and which replication strategy is suitable for which use cases. During actually we have a poll coming up immediately, don't we? We do. There it is. Ah, that's an interesting result. Thank you very much. Okay, so when I was preparing this, I realized that, it's good to talk about the specifics when it comes to synchronous, asynchronous, and multi-master. But actually, there are several ways of replicating data, and it comes out to 10 different ways of replicating data. There's probably more, but these are the ones that are documented and that I know of. So shared disk failover is the first one, file system replication, and then the four that are native to Postgres, so wall shipping or wall archiving, streaming replication, as it's also called, the next one, and then streaming replication with synchronous commit, and the last one being the native logical replication. And then again, a few non-native ones, trigger-based primary standby replication, SQL-based replication, and then multi-master replication, asynchronous and synchronous multi-master replication. I'll go through all of them. let's see. Yeah. One thing that I'll try here is to not mention any products. That way I don't forget anyone that should be mentioned. If I mention one, then I should mention all of them, and it all becomes a bit of a problem. So one more poll here before we get going. Um, if you're using replication, which ones are you using? None, native, all archiving, streaming, synchronous commits, logical replication, and so on. Okay. So that is okay. That's interesting. That's interesting because 15% say none, whereas I think very few. What was it, Alice? Was it 70% that didn't have support for the databases? Was that correct?
Yeah, that's about right.
Yeah. Wow. Okay. Well, that makes this one this comment from me, and of course this is just my opinion. But if your data is important enough to replicate, then you should also ensure professional support for your databases, because now your data is important. It's also important for you to get out of the problems that you can't solve yourself. Um, I'll also say that it's just my opinion, but and one more thing is that I don't care where you get your support, just get it. Get it from someone who is qualified to support Postgres databases. Um, anyway, there's any number of companies. Again, none mentioned, none forgotten. Okay, so if we look at Postgres itself and how it works, I've sort of marked out the parts that are interesting in terms of replication. We have all the processes going on at the top, the postmaster, as it used to be called, and the sort of main Postgres process. And we've got the clients working with the memory and reading and writing and doing all that stuff. We've got the background writer that's writing to the data files, and we have the wall writer that's writing to the wall files. So the write ahead logs. And when of course, one thing that's important, at least for the archiving that we start with, is that once a wall file has been filled up, they are usually 16 megabytes. Once it's filled up, they do a switch that requires a checkpoint, so everything is written to disk and so on, and then we do a switch of a wall file to the next wall file. That fires off the archive command that is there for you to call a script or to run to write a one-liner or something with the purpose of copying the wall file that has just been switched away from to somewhere else. That's why I have this cloud with a not here, usually to a network drive or something like that. Okay, so looking at the ways of replicating, the things that are of interest to us, of course, is the WOL files and the archive command. Starting with some of the non-native ones, though, shared disk and disk replication. So the idea here is that you have your disks, a network disk with your database data on it, the wall files, the data files, everything is on a networked disk. And you just have one VM, or usually it's a VM, or it could be a Kubernetes node, or whatever, Docker or something like that, that's reading and writing to that disk. And if that one fails, then you switch over to another one. usually in that kind of setup with VMs, you'd have two VMs set up, and only one of them would be actually be accessing the folder with the data. A folder is a misnomer because you could have partitioned data. Anyway, only one is accessing the database data, the stored data at a time. So that's shared disk, and then disk replication essentially mirrors that into a double setup where you do a disk replication, so a hardware disk replication of the network disk to another network disk, and then you can set up from there. So you have a disaster recovery and so on. And it's worth noting here that none of these servers, the VM3, VM4, are actually running. They can't run and access that network disk without generating corruption. So none of them are working or running when they're in standby mode. So this is what we call a cold standby. So the thing that I think is the biggest vulnerability in a setup like this is that if you have a corruption on your disk that could come from a failed device or something like that, it's just a write error, then the hardware replication wouldn't know that this is actually not what's supposed to be replicated. And so that replication just jumps over to the next disk, which means that file corruption in this kind of setup is actually a major concern. So for all of these use cases, I will do this. I'll talk to the use case and where it's good, and I'll speak to the good and the bad on both on all of them. So in this one, well, yeah, I know it's a bit provocative, but the only good thing I can say about this is that it kind of works. There is no overhead on the primary database, which is a good thing. It's easy to set up, and you can't lose a transaction because you're writing to the same disk. So there's no concern about missed writes and things like that. But on the other hand, there is, because as already mentioned, if there is an IO error, then that IO error actually ships to your disaster recovery site. So, and another thing that's worth mentioning here is that anytime you do a failover and one of the other VMs starts up, the first thing that happens is that the database notices that it's in a failover scenario, so it needs to do a recovery. That recovery can take a very long time. If you have some huge updates happening when the running database fails, all that needs to be rolled back before you actually open the database. So it could take a very long time for the database to actually start and accept connections. So some call this high availability. I don't really agree that it's high availability. It's at best it's availability. So that's shared disk and disk replication. Now, going to the native ones, what we have here is a sort of wall shipping. And we have sort of transactions that are committing, and we're filling up our wall file, and now we switch to a new wall file. And that fires off the archive command, which copies the shared the old wall file to a shared archive, and from there DBO2 over here, which is in standby mode, picks up that wall file and copies it, and uses the restore command to copy it to its own repository, and uses it as a recovery input. When a database is Postgres database is in recovery mode, it will always run through and look for wall files in this local directory. It will look for archiving using the restore command to try to copy a file, and it will try streaming as well. So if streaming is not set up, that's easy, but it will always go through this loop of looking for data in these places. So that's archiving, and yeah, at the end, the transactions are restored into the standby database. But it only happens when we switch wall files, right? So this kind of replication is, again, it's easy to set up, and it's easy to have this copy of the database. And it's fine in the cases where the standby doesn't have to be completely up to date. If you're using this as a read-only source, for instance, so you have a hot standby, this is fine if what you're shipping is today's data, and the only thing you need to do to do reads on is yesterday's data, for instance. Then this is an absolutely perfect kind of replication setup. And it's also in the cases where you have a network setup that prevents you from streaming data, but you can write to a network disk that then is shared between two databases, then this is a good way of solving that problem, because you can't do streaming replication because your communication between the databases is prohibited by the network setup. So again, this has a very low impact on the primary server, because all you're doing is copying the wall file. Standby can be used for read-only queries that don't need to be completely up to date. There is a risk of data loss, though. If you're using this as the only standby, then everything that's written to the existing wall file, the active wall file, if you have a complete loss of the DB01, so your active server, so if that one is completely lost, then all the transactions that were written to the wall file are not available. You're never going to get them back. So you have that risk of loss. You can tweak the checkpoints. There is an archive timeout that can be tweaked. It's usually not a good idea to set it very low, because you're basically just sending wall files that are empty, and they're still 16 megabytes. There's just no data in them, so you're filling up your archive very quickly with no data whatsoever. So it is possible to tweak, but you have to be careful with this. So next one is wall streaming. In this case, we have a new process, a wall sender and a wall receiver that's sending, reading from the wall file and sending the physical blocks to the wall receiver. We can still have wall archiving running. It's not a problem, because of, remember, the loop that the database is running through. So in this case, when a transaction commits, it's transferred and applied. But notice that it's not on the same line. It's asynchronous still, but this is what we're doing. So it is an asynchronous way of transferring data. What changed there? Oh, never mind. So this is the the type of replication that we see most, and the one that we tend to recommend for almost all use cases. It still doesn't really have that much of an impact. Sure, you have a process that's running there and reading the WAL file, but it's not a huge CPU load. The standby is almost up to date, almost being, within a few milliseconds. So you're very close to RPO equals 0. So it's a very, very good setup. The bad thing is, of course, that there is this small window of opportunity or a risk of data loss, because once things are written to the WAL file, you still need to pick it up and send it. And so these transactions, complete loss of the database, there are these transactions that may be lost because it hasn't been shipped yet, so it hasn't been streamed to the standby database. And the other thing is something just to be aware of. It's not really a bad thing, but you do need to have open communication. So you need to have port open in a firewall if the two databases are not in the same subnet. So the next one is synchronous commit. Oops. In that case, when a transaction commits, it's transferred immediately to and applied. Actually, what you do in synchronous commit is that you set up a requirement on the database that says that when you set up synchronous commit, or you set up synchronous standby names, as it's called, the thing that happens is that the database, the primary database, will synchronize the transaction with the standby database, and the commit will not return until the data has been applied. There are different values there. I'm not going to go into the details about the different kinds of values available for synchronous commit, but the idea is that the data has to be available to the standby database, and then the commit returns. So the application then has confirmation that this has committed. So we'll go through that and go to here. So this is used in situations where you absolutely need to have a standby that's fully up to date at all times. That could be because of the application that's reading the data, or it could be because you want to prevent any type of data loss. It's essentially the same as asynchronous replication, but you have that additional benefit that now you can't lose data. Trouble with this is that unless you have several standbys and you've set this up correctly, then if the standby becomes unavailable and you only have one, then all commits hang. Every single commit will not finish until the standby is brought back up and has received the data. That's part of the definition of synchronous commits. And so the workaround there is to have several databases as standbys. I'd say at least 3. 2 is good, 3 is better. And then set it up in such a way that you say that 1 or 2 of those databases have to have the commit before the commit returns. That way you're secure, but it just requires more servers. And so the next one here is native logical replication. In this case, you're not sending physical blocks anymore. in streaming replication, you're actually the thing that's being sent is information on changes in the data file. So this block has to look like this block has to look like this, and so on. So it's a complete copy of the data. Of the data files are essentially copies of the ones from the primary database. In the case of logical replication, what you're doing is you're sending inserts, updates, and deletes. So what's happening is that the wall sender is actually decoding the wall file and saying, okay, so this translates into an insert, this translates into an update, and so on. That's what's happening. And then on the other side, the replication worker is performing those updates, of course, bypassing triggers because it's a replication user, so all triggers are being bypassed. And in this case, you can set this up as synchronous, you can set it up as asynchronous. So in this case, both scenarios work, that you can have an asynchronous application, or you can have a synchronous application, and the same caveats apply to this as to the other one. So here, the use case is that you can update, you can use native replication to replicate an entire database if you wanted to. And it's sort of a discussion whether it's faster or slower than streaming replication. I think it very much depends on what's going on the database more than anything else. But it's certainly something worth testing. The good thing here is that this can span Postgres versions, because logical replication, that protocol doesn't change. Whereas with major versions of Postgres, the data files and the format of the wall files or the format of the data files, anything can change. But with logical replication, that protocol is not going to change. So you can actually do a replication from a Postgres 13 to a Postgres 14. And continue to do that. It's not a problem at all. Another good thing, and I see that I didn't move my good stuff into the evaluation side here. Sorry about that. It's the way that you use this is, for instance, to consolidate several data sources, for instance, for a BI or reporting server, a staging area for a data warehouse or something like that. You can use native replication for that. It's also good in situations where you have where you need to do a major version upgrade, for instance. So you create a new database, that's the new version, and then you set up logical replication to move the data across, wait for it to synchronize, and switch off the old database. That way you can do a major version upgrade without needing downtime, at least not hours of downtime. So the problem with native logical replication is that there's no DDL. So new tables, for instance, are not going to be replicated. You have to set that up manually. Any changes to the tables, you're going to have problems. You add a column, you change a column, you remove a column, then you have a problem with replicating that, unless you perform all the DDLs manually on the standby server. As it says here, you can use insert, update, delete, and truncate. But again, there's a problem here because the only thing that's actually available is insert, unless you have what's called replication or replica identity. And that could be a primary key or something on the table. It's something that identifies the row. Now, replica identity could be all. So it could be the full row, but it's not efficient. But it is something that you need to bear in mind, is that you have to have some kind of primary key or whatever on the database. Oh, failure in my animations. Okay, and so we come to the final form, and none of these are native to Postgres. So the first one is trigger-based replication. It's fairly easy to understand what this is. And 1 second, please. Um, and here I'm trying to be as vague as possible, because there's so many different implementations of how this works. We have some. There are some that are open source, other companies have solutions, and none of them work the same. But in the end, it comes down to this: something triggers will capture the data changes, and then something picks up those changes and push them to another database in the same, usually in the same form as with logical replication. So insert, update, and deletes. The good thing about this is that it's easy to understand, and sometimes it's easy to set up. There are a lot of these products that have a lot of ways of replicating data, and replicating data from several data sources, some of them not Postgres, which with any product that has a lot of options, it also becomes complicated and complex to set up. So that's why I say it's sometimes easy to set up, but in principle, it's easy to understand. It tends to be fragile. It has the same problems that usually it has the same problems as logical replication does, in the sense that it doesn't update the table. So you have to sort of, when you want to do updates of the tables and do DDL on the tables, then you should have to shut this off and then perform the updates and then set it back up. Because otherwise, if you only update on one side and then something is being sent, then oh no, you're in trouble, because it can't insert the data on the other side, and so on. So there's this kind of synchronization problems in this kind of replication setup, and it tends to be slower than any wall decoding solutions because of the triggers. So this has an impact on the primary database, because you have triggers that need to fire and have to insert data somewhere. Next set is SQL-based replication. In this case, you have a proxy that functions as a connection pool, and then captures all the data changes. So it's capturing all the update statements that are being sent to the database, and replicates those exact SQLs to the other database. This is great. It's easy to understand. It's usually easy to set up, and a SQL proxy like this, apart from being a connection pool, it can also provide read-only routing. So it can do round robin on any of the replicated databases and so on. So in that case, it's absolutely great. The problem with this is that identifying what is a SQL that's an update statement. So which are not. The simple ones are insert into, update, truncate, create table, dot table, and so on. Those are definitely things that need to be replicated. But what about this? Is that an update statement, or is it just a function call with no side effects? You don't know. So the proxy has to do one thing. It has to send this as well to all the replicas. Um, and that might be unnecessary traffic, but it can't tell, right? So it just has to do this. And if your application uses a lot of this, then is there a benefit to using a SQL proxy? Maybe, maybe not. Okay, so multi-master active, as we call it. In this case, we have several databases, all of them being active or primary databases, as it's called, and all of them are sharing data between them. Again, several products that can do this. And the good thing is with this is that it's highly available in the sense that none of these databases need to change mode. They're not in standby mode, any of them. So if you need to do a failover, you just switch to another database. Applications can access all of these databases. They can update all of these databases. In some setups, you have a lead master or several lead masters that tends to be the ones that you want to update, but you don't really have to. It's sort of all of them are available to do this, and there is a certain level of scalability in this kind of setup. In that as you can update all of the databases, if your triggers are very CPU intensive, then using them as a sort of CPU multiplier for your application is a good way of doing this, because once the data is replicated to the other databases, it tends to bypass the triggers. So there is a sense that you have more CPU available. But as some of my colleagues say, you can't cheat physics, right? But at some point, you're just going to run out of CPU anyway, because even though you have several databases to update, all the data has to be replicated to all of the databases. So that traffic in itself requires CPU. So there is a degree of scalability, but it's not the primary, at least not in my view, it's not the primary focus of this kind of setup. The bad thing is that this can be somewhat difficult to configure correctly. It is a distributed system. They generally tend to be a bit more complex than the usual non-distributed systems. Logs are not distributed, so select for update, for instance, is not going to work. That row will be logged on the database that you're currently logging into, but if someone logs into another database and starts updating, they're not going to see that log, so they can easily update the same row that you're trying to log. So that kind of coding in the applications is not going to work. You can't secure in that way. You have to use some other means of securing your data and locking them for update. And another thing is conflicts. So if you're updating the same data on several databases, you are going to have conflicts. So that will require conflict handling. That conflict handling requires CPU, it requires special attention, and so on. So beware of this. And any solution that you, I'd say that the most important thing here is that these conflict management, when you pick a solution for multi-master, you have to pick one that has solid conflict handling and, as I call it, avoidance. That could be special functions that performs two-phase commit in specific scenarios. It could be specific types of sequence handling and so on, so that you don't run the risk of inserting data with the same with the same primary key and so on. These things have to be handled. And the last one I'm just going to cover down here. because a fully synchronous multi-master, it doesn't exist at the moment. Multi-master is inherently asynchronous in Postgres. Um, Synchronous multi-master is a thing that's one of our competitors do. And the reason why they can do that is because they've rewritten most of the operating system as part of the database, so they can share memory and they can share disks without errors and things like that. Postgres isn't built that way, so this kind of setup is not possible. Also, in the case of this kind of synchronous multi-master, these databases have to be very close to each other and connected with a very fast network. In asynchronous multi-master, these databases can be on different continents if you have to do that, and it will still work. So those are the 10 different ways of doing replication. And the final poll here is, so now that I've run through them, which one would you prefer? I'll leave you just a few minutes to answer that. Yeah. Yeah, so native world streaming is definitely the winner, and I agree with that. It is by far the best and the easiest way to ensure replication of your databases. So yeah, good. So a few references. I expected that I wouldn't have time for a demo. I don't know if we have time. We might, but I've forgotten to set up my server. You'll have to bear with me for a minute if we're doing a demo. But I have a script that demos the native versions of replication. So wall archiving, wall streaming, synchronous commits, and logical replication. And there's a README in there and in this, sorry, in this one. In the demo script, there's a README that explains how to use the script and how to a few commands to sort of show how they work. There's a nice blog post by one of my esteemed colleagues. It's called Replication Engine Potpourri, that goes through a lot of the strengths and weaknesses of the different products that I've tried not to mention here. And there's also one called Defining High Availability that goes through what high availability looks like in Postgres in general. And then there's one that's sort of a caution, nominally bidirectional, which is a setup that looks on paper looks good, but isn't for a multi-master setup. And with that, I'll ask if there are any questions currently.
Thank you, Michael. Yeah, we do have a couple of questions for you here. So the first one is it possible to set up multi-master replication using PG Logical?
Yeah, for those who don't know, PG Logical is was an open source project from Second Quadrant that was a receiver for logical replication and had some features in there. The version 1 was open source, version 2, 3 are not open source and are part of BDR, bidirectional replication. And now I'm making the mistake of mentioning products. Sorry. But PG logical, yeah, actually the blog post normally bidirectional mentions PG logical and why this is not a good idea. So if you're interested in using PG logical for multi-master, you should read that blog post, because it goes into very, very good details about why this is not a good idea to use PG logical for that. You do need a real multi-master product to do this, because of things like conflict management and conflict avoidance and so on, these things. Okay, next question.
Yeah, so then we've just got another question, which is, why has the Postgres project never included automatic failover or a single connection string for streaming replication? I appreciate there are third-party solutions, but these add complexity.
Yeah, I agree. Why? That's a good question. Why? I think Postgres is built in the same way that many Linux programs are built. It does one thing and it does it well. It's a database. It stores data. It accepts updates and so on. But it doesn't provide connection pooling. It doesn't provide failover and so on. So I think it is mainly I would guess that it's because of that focus on doing one thing well that it doesn't provide it itself. But I agree, there are third-party products out there, and some of them are open source, and some of them work very, very well. So, but yeah, I agree, it does add a bit of complexity, but it also adds choice, freedom of choice. You don't have to use the failover implemented in Postgres, because it doesn't have one. You can choose which one you want to use, and there are definitely benefits and differences between the different implementations.
Thanks, Michael. And then another question. Bacado is mentioned as a multi-master solution on PostgreSQL.org. What is your view on this solution?
Yeah. Actually, that's part of the replication engine potpourri. It's one product. It's a very good product. There are other products out there that do the same, and I have absolute respect for the Bacado team for what they're doing. So, but read the replication engine potpourri for information. I think it does mention Bacado in there. So that's, yeah.
Okay, thanks, Michael. That's all the questions we've had through so far, and we've got about 10 minutes left of the webinar if you did want to do a demo.
Yeah. See if I can. I'll stop sharing for 1 second.
Okay. Whilst you're setting that up, I will just say we are running a prize draw for everyone who's attended the webinar today. So there's a prize of a gift voucher to the value of €25. So we'll just be picking randomly after the webinar. So make sure you check your inbox after the webinar and you might be our lucky winner. So yeah, we'll be in touch today if you're the winner of that. Other than that, I'll let you do your demo, Michael. Have you got everything you need to be able to run it?
Oh yeah, I need to start my server here. Right. Let's see if I can get everything up and running. Should be fairly easy to do. Right. Whoops. Sorry. That's what happens when you press the wrong buttons. There we go. Okay. So here we are. So I have this set up with replication sh, which is part of the demo script. And what I can do with that is I can start by listing the databases that are available, and I only have one, the main database, which I've shut down because I'm not going to use it. I'm going to create a couple of other databases. So this is a Ubuntu setup, so I'm just using the scripting provided by the Postgres development team for Ubuntu, and Debian has these nice pgctl command, no, not pgctl, but pgctl cluster commands for a lot of things, create and so on. Great tools. So I've created 4 databases, and now what I can do is I can remind myself how to do this. What I'll do is I will go and I will enable shipping. That's not what I wanted. I wanted to do that instead. So I'll go through what's going on up there in just 1 second. Just need to set these up. There we go. Vagrant replication. Do I have a, don't I have a, okay. Right, so we'll go through what's going on up here. So what I'm doing here is it starts around here where I have the clusters showing up. Larger text, difficult to read. Yes, I can do that.
Thanks, Michael.
Boom. Like that. And hopefully this is going to work. It's just, oh, it's just adding to one of them. That's annoying. Okay. So I'm going to do that. And then this one. Is that better? Okay, thanks.
Yeah, that's better. Thank you.
So where is this? Yeah, here it is. So I have my 4 databases, and I'm creating a table on, so this is the port number. So this is on DB01, I'm creating a table, creating one more table, and I'm inserting some data into that table just to have something to show. And then I'm setting up, I'm running a PG switch wall, which is actually a very good example of a command that looks like just a normal select statement, but it isn't. It's just how Postgres works, that you can do these things, and those functions can do a lot. So what I'm doing then is I'm stopping the DB02. I'm shutting that down, and then I'm removing the entire directory. I'm basically deleting the database completely. Then I'm doing a base backup from DB01 into DB02's folder. So I'm making a copy of the database. I'm setting up standby signals. So now I'm telling the database that it needs to be in standby mode. And I'm setting up a restore command here. So what we have now is 5433. Oops. I thought I had a command to actually log into the database, so I didn't have to remember how to do that. Actually, what I need to do is I need to switch to Postgres. That's one thing I need to do. Yeah, there it is. So I'm going to log into DB02 here. And on this one, I'm going to log into and if I'm, yeah. So what did I log? I logged into DB01 over there. I'm going to log into DB02 here. So here I have my table 1 is available, and I'm going to watch that table. And then on this one, I'm going to insert data. If I'm lucky, then I actually have that. Don't have that. So I'm just going to insert directly. Table 1, I'm going to insert a 2 into that table. And I always forget to write values. My entire career, I've forgotten to write values. It's incredible. And as you can see, no data is being replicated until I either fill up the wall file, which is going to take a while, or I do PG switch wall, which forces Postgres to switch to a new wall file. And once that happens, then the data should be updated on the other side. There it is. So that's streaming or wall shipping, as it's called, or wall archiving. Then in this one, I can then enable streaming instead. And I'm still going to use the same, just the same 2 databases to set up streaming replication. And what I'm doing is I'm creating a role. Whoops. Oh yeah, I need to restart the database, of course. So I should shut that down, and I could feasibly log in again. Yes. And I will set up my watch on the table again. So what I'm doing in here is that I'm creating a role that I'm going to use for replication. That's usually a good idea to have a specific user that's the one performing the streaming and logging into the database. So I'm setting up this rep user. I'm creating a replication slot for that. I'm also setting up replication slot for DB04. So I now have 2 standbys. And then I'm setting up listen address on DB01 on my master, because now I need to be able to log into the database from somewhere else. And I'm setting up a primary slot name on DB02. Yes, no, yes, yes. On DB02, I'm setting up, it says DB02 here. I'm using the primary slot name, and I'm setting up connection info. So now this database will create its streaming replication process and log into to DB01 and have that one create a wall streaming sender and retain the wall files based on this primary slot name. I'm setting up for DB04. I'm doing the same. So this one is essentially a copy of DB02. And I'm restarting the databases, and that should result in data being streamed to the other database. Maybe I want to log in again because there we go. And I didn't have to do a switch wall. Data is streamed straight to the database, and it looks immediate. It's almost immediate. The only thing that isn't immediate is that it's happening as the commit is being performed, and we're out of time.
Thanks, Michael.
This is why I didn't want to do a demo, but as you can, at least I've shown how these tools work, the script works. So you can go ahead with the rest. It's all in the
Yeah.
README, and it's public. So go ahead and download it and have a look.
Brilliant. Thanks, Michael. We'll have to do another webinar so you can do some more of the demoing. Okay, great. Well, thank you everyone for joining. We will be sharing the recording and the slides as soon as possible. But that's everything for today. So we wish you all a great rest of your day and thank you.
Thank you, everyone. Bye-bye.